Okay, so now we're going to talk about the remainder theorem, the factor theorem, and rational zeros. Okay, so the remainder theorem. What I'm going to do is I'm going to take a quadratic, nice simple quadratic. I'm going to use the right tool here. Let's say x squared plus 3x plus 8, and I'm going to divide it by a linear factor. So I'm going to divide it by x minus 2, okay? Now I'm going to use synthetic division because I'm dividing by a linear factor, and that actually ends up being 2. Remember, this has to be the root. This would be a 1, a 3, and an 8, right? Now, then what I'm going to do is actually do the division. So I just bring down the 1, multiply. 2 times 1 is 2, and I add. 2 times 5 is 10, then I add. Now remember, this last thing is actually the remainder, which is 18, okay? Okay, so now, skipping ahead. If I say that this is some function f of x equals x squared plus 3x plus 8, watch this. What would happen when I plug 2 in? Well, it would be 2 squared plus 3 times 2 plus 8, aka 4 plus 6 plus 8. 4 plus 6 is 10 plus 8 is 18. Hey, that's the remainder. So how is this related? If I'm evaluating a function, that is, if I'm plugging a certain number in, is that the same as doing a synthetic division of that and then using the remainder, or does the remainder end up being that? That's what the remainder theorem says. It says that when you actually do divide by some factor, then that, and the remainder ends up being what that function is evaluated at that point, okay? Let me give you another example. Find f of 3 for this, meaning I could plug 3 in, but let's say I didn't want to plug 3 in because I'm feeling like I don't want to grab for my calculator because 3 to the 4th sounds like a big number, as does 3 cubed and all that. So here's what I can do. I can use the remainder theorem to help me out. I want to evaluate at 3, so that means I'm going to put 3 here. And then I'm going to fill this out. So 2, that's negative 3. There is no squared term, so I need to make sure to fill that in. That's a 0, right? So I got a 0x squared in there I got to be careful about. And then a 2 and a negative 5. Now, my argument is that the remainder, this last number here, is going to be what the function is. So bring down the 2, multiply, add. 3 times 3 is 9, add. 3 times 9 is 27, add. What's 3 times 29? That's a lot like 3 times 30, but 3 less, isn't it? So that turns out to be 87. Negative 5 plus 87 is 82. Now, just to prove this, I'm going to go ahead and figure out what f of 3 is, which is 2 times 3 to the 4th minus 3 times 3 cubed plus 2 times 3 minus 5. And if all is right with the world, then I end up with 82. So 3 to the 4th turns out to be 81 minus 3 cubed is 27. 2 times 3 is 6. I think you can see why we might use this, right? So this is 162 minus 3 times 27 is, that's 75 plus 6, or 81 plus 6 minus 5. Okay, let's hope this all works. Hey, wait, 162 minus 81, that's just 81. Plus 6 minus 5. Hey, that's 82. Ding, 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 it works. So does the remainder theorem work? Yes. So the remainder ends up being, well, what we would get if we evaluated the function at that value. The factor theorem. The factor theorem says that if I were to take, say, some sort of function, minus 4, and to divide it by its root, so one of its roots, so let's say that ends up being 1, what happens? Well, we know that x minus 1, because if we factor this, this is x minus 1 times x minus 4, right? Or sorry, x minus 1 times x plus 4. So what happens? So this root is 1, right? Remember, you have to divide by the root. So we get 1, 3, negative 4. What does it mean? 1 times 1 is 1, 3 plus 1 is 4, 1 times 4 is 4. And so it goes in evenly, which means that we get a remainder of 0. So if a number is a root, then the remainder, when dividing by that root, is 0. And it kind of works both ways. What if you divided by something and discovered that the remainder was 0? What does that tell you? That it's a root. So that can be kind of handy because then if you know what a root is, then you can pull it out to simplify things. Or it means that you could test some values and figure out what a root is, and the one that has a remainder of 0 is indeed one of the roots. Okay. Now, rational zeros. So it turns out that if we are looking at something like 2x minus 3 times, let's say, x plus 4, right? When we are solving this, so this is some function y, right? So we know that one of our zeros is when 2x minus 3 equals 0. We know the other one is when x plus 4 equals 0. So that's easy. It's x equals negative 4. And x equals 3 halves. That is, we add 3 and we divide by 2, right? So it turns out that in general, if we have some sort of root ax minus b, right? This is ax minus b, it just happens to be 1, right? That somehow these numbers are related to the first and the second terms of the coefficient of the linear factor and this constant term by division. That is, we're dividing specifically by this. And to make matters worse, it means if we think about the multiplication, because this is going to be 2x squared, right, minus 3x plus 8x, so it's going to be plus 5x, and then this is going to be a negative 3 and times 4, so minus 12. What it means is, and this is, once again, we're not looking for a terribly rigorous proof, we're kind of just noticing some things here, I hope. It means that the roots are going to be related to these coefficients here, that is the lead coefficient and the constant term. It's specifically related to the factors of this, which are 1 and 2, and the factors of this, which are, well, some of the factors are 1 and 12, 3 and 4, 2 and 6, right? Those are all different factors, combined in certain ways. So if you look carefully, if you look at these factors, and because of how we're doing it, we're always going to take the linear factor over this, is there a way to combine these factors and these? Nice that there's only 2 to pick from, isn't it? To get negative 4, for instance. Now remember, these could be positive or negative. In other words, you could have a positive 1 and a positive 2, or you could have a negative 1 and negative 2, so we had to kind of account for that. This could be negative 1, and it could be positive 12, or could it be positive 1 and negative 12. Now to simplify things, normally what we do is we just kind of write plus or minus. I'll show you that in just a sec. But the notion is, if I were to take, say, I don't know, how about 12, or I'm sorry, how about 6, and divide it by negative, wow, what am I thinking? How about 4 and divide it by negative 1? What is 4 divided by negative 1? Well, that's negative 4. So somewhere amongst these numbers, the zeros are kind of hidden, if you will. 3 over 2. Hey, look, there's a 3, there's a 2. Or remember, because it could be combinations of positive and negative. It could be a negative 3 and a negative 2. But either way, I get this. So what this means is, the practical import is that if I've got some polynomial, right, plus bx squared plus cx plus d, right? So some sort of cubic, right? There are going to be factors of this, and there are going to be factors of this. So the possible rational zeros would be related to the factors of the constant term divided by the factors of the lead coefficient. So when we say rational, by the way, we talk about rational numbers. We're talking about division, because if you look at these, both of these are rational numbers. That is, you can express them as a fraction, okay? Let's do an example. Maybe that'll make things a little bit clearer. What if I had 3x squared plus 7x minus 4? Keep it simple, right? Yes, you might say I can directly find this, but what are some possible numbers they could be? So we look at the lead coefficient, and we look at the trail, and we list all the factors. Easy, 1 and 3. Pretty easy, 1 and 4, 2 and 2. Hopefully you remember factoring. Now remember, there could be a combination that are positive or negative, so to cover all our bases, we just take positive or negative, positive or negative, positive or negative, positive or negative, positive or negative. This may seem like overkill, but it's not as bad as you think. Then we take all possible combinations, because remember, it's always going to be of the constant term, so the possible zeros, the zeros, are going to be the constant term, that is the plain old number, divided by the lead coefficient, right? So the constant term, so for instance, we just do all the possible combinations. Well, we could pair the 1 with the 1, so it'd be plus or minus 1 over 1. We could pair the 4 with the 1, so it'd be plus or minus 4 over 1. We could also pair well, let's get all the combinations. We could pair the 1 with the 3, right? So it could be plus or minus 1 over 3. We could pair the 4 with the 3, so it could be plus or minus 4 over 3. Now there may be some duplication. You'll see that in just a sec. Well, actually, you won't see that in just a sec. We won't have any duplication in this case. 2 and 1, right? So plus or minus 2 over 1. Oh, we are going to have duplication, 2 over 1. Or it could be plus or minus 2 over 3. Now let's clean this up a little bit. Most people would write plus or minus 1, plus or minus 4, plus or minus 1 over 3, plus or minus 4 over 3, plus or minus 2, and plus or minus 2 over 3. Now, I should point out these are possible rational zeros, okay? Meaning, positive 1 could be a 0 or negative 1. You don't know, it's not a guarantee, but these are the possibilities. Now, unfortunately, this doesn't cover imaginary numbers or complex numbers. We'll learn about that later. But this is at least one way to find values to test, because then if you thought, oh, maybe it's 4, and you could divide by 4 and see if you get no remainder, right? So this is just one way of listing off what some possibilities are for this. And this concludes the factor theorem, the remainder theorem, and possible rational zeros.